Now potential due to a system of charges. Suppose here we have a system of n charges. The charges are Q1, Q2, Q3 up to Qn. And having the position vectors with respect to origin of Cartesian coordinate system are R1, R2, R3 up to Rn respectively. And now we want to find the resultant electric potential of this entire system of charges at point P, which one have the position vector R with respect to the origin of Cartesian coordinate system. Clear to all of you? Now here the concept that is very simple. First of all, we have to take the potential of charge Q1 at P, then charge Q2 at P, then charge Q3 at P, up to charge Qn. We have to carry out the calculations. Then after, by taking the summation of all these, we will get the resultant potential at point P. Now see, suppose first we think about the potential of charge Q1 at point P. Now see, here charge Q1 have the position vector that is R1. Position vector of point P that is R. It implies that position of point P with respect to charge Q1 that we can represent by R minus R1. Clear? Now, for a point charge, the electric potential that is kq upon r, where r that is the distance of that point from the point charge. Now here the distance of point P from point charge Q1, that is the magnitude of r minus r1. So we can write V1, the potential due to charge Q1 at point P, that is kq1 upon r minus r1 magnitude. Then potential due to charge Q2, that is V2 equal to, similarly we can write kq2 upon magnitude r minus r2, and up to Qn, we can write the potential due to Qn, that is Vn equal to kqn upon r minus Rn. Clear to all of you? Now the resultant potential at point P, that is V at point P equal to V1 plus V2 plus V3 up to Vn. So we can write potential at point P that is equal to kq1 upon magnitude r minus r1 plus kq2 upon magnitude r minus r2 plus up to kqn upon magnitude r minus rn. So we can rewrite it like this: potential at point P, V at P, that is k sigma I equal to 1 to n qi upon magnitude r minus ri. Clear? This one is the resultant potential at point P due to entire system of charges. Now, next topic, that is electric potential due to volume distribution of charges. See, તમને જો યાદ હોય તો આપણે ફર્સ્ટ ચેપ્ટરની અંદર ઇલેક્ટ્રિક ફિલ્ડ ડ્યુ ટુ અ સિસ્ટમ ઓફ ચાર્જીસ ડિસ્કસ કરેલું. તો અહીંયા આપણે ઇલેક્ટ્રિક પોટેન્શિયલ ડ્યુ ટુ અ સિસ્ટમ ઓફ ચાર્જીસ ડિસ્કસ કર્યું. પછી ફર્સ્ટ ચેપ્ટરમાં આપણે ઇલેક્ટ્રિક ફિલ્ડ ડ્યુ ટુ લાઇન ચાર્જ ડિસ્ટ્રીબ્યુશન, then electric field due to surface charge distribution, the electric field due to volume charge distribution that we discussed. In the same manner, here we have to discuss the electric potential due to volume charge distribution or volume distribution of charges. Line અને surface અહીંયા નથી આપ્યું, પણ વોલ્યુમ નું આપણે અંડરસ્ટેન્ડિંગ લઈ લઈએ એટલે લાઈન કે સરફેસ માટે સેમ ટાઈપ ઓફ કોન્સેપ્ટ એપ્લાય કરાય. Now see here. Suppose we have a volume charge distribution and we want to find the electric potential at any point due to that particular volume charge distribution. Now, concept that is a simple one, which we discussed in chapter number 1. For this given volume charge distribution, we have to divide this entire distribution into so many infinitesimal small volume element. Suppose here we consider one volume element, which one is possessing charge dq, and suppose its a position with respect to the origin that is equal to r dash. Now, due to this particular infinitesimal small element, the potential at point P having position vector r, that we can simply write like this: dV at position r, that is equal to k dq upon magnitude r minus r dash. But now dq is how much? So here suppose volume charge density, that is rho r dash. So we can write charge per unit volume, that is rho, then charge in given volume is how much? So we can write now k, now dq, that is rho at position r dash into volume element. Here in text the volume element that is represented as d tau dash and magnitude r minus r dash. Clear to all of you? Now in this manner, if entire charge distribution is divided into so many infinitesimal small volume elements, and for each volume element we calculate the potential at point P, and then after if we take the summation, then we will get the resultant one. It implies that here we can take the integration because charge distribution is continuous one. So resultantly we can write the potential at point P having position vector r, that is equal to k, that is 1 upon 4 pi epsilon 0. Integration should be carried out over the entire volume, rho at r dash into d tau dash upon magnitude r minus r dash. Clear to all of you? Suppose we want to find the electric potential at any point due to line or linear charge distribution, then very simple thing. Integration should be carried out over the line. Here we have to take line charge density or linear charge density, and we have to consider line element. Suppose we have the surface charge distribution, and due to that surface charge distribution we want to find the electric potential at any point, then we have to consider so many infinitesimal small surface elements. And we have to consider the surface charge density. So concept that will remain the same one. Clear to all of you? Next topic, that is electric potential due to uniformly charged spherical shell. Now see, in a previous chapter, we discussed this thing. The charge distributed on the spherical shell behave like a point charge concentrated at the center for any point which one is outside the shell. It implies that if total Q amount of charge is distributed on the spherical shell and we want to find the electric potential at point outside the shell, then for that this entire charge distribution will behave like a point charge. Now see, suppose the radius of the shell, that is capital R, and we want potential at a point which one is at a distance small r, where small r is greater than capital R. Then we can write simply that is kq by r. That is kq by r. Suppose we want potential at the surface of the cell. Now at the surface we can take small r, that is equal to capital R. So we can write that is kq upon capital R. Clear to all of you? Now see here. When we say at the surface, the potential, that is kq upon capital R. As per definition, potential means what? Potential means the total work done in bringing unit positive charge from infinity to a particular point against the field is the potential at that point. હવે આપણે એવું કહીએ કે આ સેલની સરફેસ ઉપર ઇલેક્ટ્રિક પોટેન્શિયલ કે ક્યુ અપોન કેપિટલ આર છે. તો એનો મિનિંગ એ થયો કે total work done against the field to bring unit positive charge from infinity to the surface of this sphere, that is kq upon r. હવે માની લો કે તમારે આ સ્ફેરિકલ સેલ જે આપેલી છે એની અંદરના કોઈ પોઈન્ટ ઉપર પોટેન્શિયલ ફાઇન્ડ આઉટ કરવું છે, અંદરના કોઈ પોઈન્ટ ઉપર, રાઈટ? એટલે જુઓ કે આવું કોઈ પોઈન્ટ લઈ લઈએ આ જગ્યાએ. તો સરફેસ સુધી તો આપણે યુનિટ પોઝિટિવ ચાર્જ લઈ આવ્યા અને એ માટેનું વર્ક ડન બી ગણી લીધું અને that is kq upon capital R. તો હવે આપણે એક કામ કરીએ. From surface to this particular point inside the spherical shell, we displace the unit positive charge and let's calculate the work done against the field. તો એ કેટલું આવશે? 0. કેમ 0 આવશે? Because in chapter number 1 we discussed this thing. The electric field at any point inside the spherical shell, that is 0. તો જો spherical shell ની inside electric field 0 હોય, then work done, that will be 0. It implies that the potential which one is at the surface kq upon capital R, that will remain constant up to center. So now we can conclude like this. at any point inside the charged spherical shell, the electric potential that is constant one and that is equal to the potential which one is at the surface of the shell. Clear to all of you? Example 2.2. Two charges 3 into 10 raised to minus 8 coulomb and minus 2 into 10 raised to minus 8 coulomb are located 15 centimeter apart. At what point on the line joining the two charges is the electric potential 0? Take the potential at infinity be 0. Okay. Now say 2-point charges, one that is 3 into 10 raised to minus 8 coulomb, another one that is minus 2 into 10 raised to minus 8 coulomb. Both are separated by distance 15 centimeter. Okay. Now here we have to calculate the electric potential at a point for which the resultant potential comes to 0. તો હવે શું થશે કે આ જે પોઈન્ટ છે એ સ્મોલર ચાર્જની ક્લોઝ આવશે બીકોઝ પોટેન્શિયલ પ્રપોર્શનલ ટુ 1 upon r. એટલે સ્મોલર ચાર્જની ક્લોઝ આવશે અને જે મોટો ચાર્જ હશે એનાથી એ દૂર હશે. ઓકે. So first we can consider like this. Suppose between these two charges, the null point is at distance x from 3 into 10 raised to minus 8 coulomb. So point P that will be at a distance 15 minus x from minus 2 into 10 raised to minus 8 coulomb. Clear to all of you? Now the resultant potential at point P that we want 0, it implies that potential due to charge Q1 that is KQ1 upon R1 plus potential due to charge Q2 at point P that is KQ2 upon R2 and that should be equal to 0. Now Q1 that is 3 into 10 raised to minus 8, R1 that is the distance of point P from charge Q1 and that is x. Then charge Q2 that is minus 2 into 10 raised to minus 8. So here with negative sign we can write 2 into 10 raised to minus 8 upon the distance of point P from charge Q2 that is 15 minus x and that is equal to 0. So now we can take k common, then take it on right hand side will be cancelled. Then take 10 raised to minus 8 common from this equation, take it on right hand side, it will be also cancelled. So resultantly we will get 3 by x equal to 2 upon 15 minus x. And now if we solve this one, then we will get the answer x that is equal to 9 centimeter. It implies that the point where the resultant or net potential becomes 0, that point will be at 9 centimeter from 3 into 10 raised to minus 8 coulomb charge, or in other words we can say it is at 6 centimeter from minus 2 into 10 raised to minus 8 coulomb charge. Clear to all of you? Now another possibility, બીજું પણ એવું point મળે કે જ્યાં resultant potential 0 આવે, which one is outside these two charges, okay, on the line joining to these two. તો હવે જુઓ, suppose point Q that is also null point, means the point where potential is 0, is at a distance y from charge Q1, that is 3 into 10 raised to minus 8 coulomb. Therefore, from charge Q2, that particular point will be at a distance y minus 15. Now at Q also the potential is 0. So we can write now potential due to charge Q1 at capital Q point, that is K Q1, that is 3 into 10 raised to minus 8 upon Y, and potential due to minus 2 into 10 raised to minus 8 coulomb, that is minus K2 into 10 raised to minus 8 upon the distance y minus 15, and that is equal to 0. Again, take K and 10 raised to minus 8 common, take it on right hand side, will be cancelled. So resultantly we can write 3 upon y minus 2 upon y minus 15, that is equal to 0. And now if we solve this one, then we will get y that is equal to 45 centimeter. Okay, it implies that we can say the another null point that is at 45 centimeter from charge 3 into 10 raised to minus 8 coulomb towards the negative charge. Or we can say that another null point that is at a distance 45 minus 15 means 30 centimeter from minus 2 into 10 raised to minus 8 coulomb. Clear to all of you? Example 2.3. Figure A and B show the fill lines of positive and negative point charge respectively. Figure is given to you, right? Now, question A. Give the sign of the potential difference for points P and Q, and for second figure A and B. Give the sign of the potential energy difference of the small negative charge between the points Q and P as well as A and B. Give the sign of the work done by the field in moving a small positive charge from Q to P. D. Give the sign of the work done by the external agency in moving a small negative charge from B to A. E. Does the kinetic energy of the small negative charge increases or decreases in going from B to A? So first we have to take the sign of the potential differences, clear? And then of potential energy difference. Now see, here for positive charge, the electric field lines are in outward direction. For negative charge, that is towards the charge. Now the points P, Q, A and B are as shown in the figure. So we know this thing. The potential of positive charge, that will be positive potential, and potential of negative charge, that will be negative potential. Now see, first thing, potential of positive charge, that is positive potential at P as well as at Q. But potential due to a point charge, that is KQ upon R, means V proportional to 1 upon R. It implies that here point P is closer to the charge compared to Q. It implies that for first figure we can write Vp that is greater than Vq. And see the second figure. Charge A is close compared to charge B. But here, why we write VB is greater than VA? Because here the potential at A is more negative compared to B. એટલે જે વેલ્યુ મોર નેગેટિવ હોય એ નાની કહેવાય અને લેસ નેગેટિવ હોય એ મોટી કહેવાય. Right? So VB is greater than VA. So for first figure, we can write VP minus VQ, that will be positive. And for second case, VB minus VA, that will be positive. Clear to all of you? Now, potential energy of any charge small q at point P, that we can write Q into Vp. So here, if we take minus Q charge at point P, then its potential energy, that is minus Q into Vp. If the same minus Q charge is placed at point Q, then its potential energy, that is UQ equal to minus Q into VQ. So the potential energy difference, if we take UQ minus UP, then that will be positive. Similarly, if we place minus Q charge at A, so at A the potential is negative, so negative, negative, positive. So UA, that is Q into VA. At B, we can write minus Q into minus VB, that is Q into VB. Okay, so in that particular case, you will get UA minus UB, that will be positive. Clear to all of you? Now, work done to move small positive charge from Q to P, that is WQ to P, that is VQ minus VP, but VQ is less than VP, so this work done will be negative. In next question, we have to move the small positive charge from B to A. So total work done WB to A, that is VB minus VA. VB is less negative compared to VA. So the answer will be positive. It implies that its potential energy increases. And if potential energy increases, then kinetic energy decreases because the total energy that remains constant. Clear to all of you? Now the next topic, that is equipotential surfaces. See, heading જ clear છે, તમને તરત ખ્યાલ આવી જાય. Equipotential surface मतलब कि एवी surface કે જ્યાં at each and every point the potential same હોય, right? So we can give definition of it like this. An imaginary surface in the given electric field for which at each and every point on that surface the potential is same one. Or in other words, you can say an imaginary surface passing through all those points in the given electric field having same potential. That is called equipotential surface. Let's try to understand this thing with example. Suppose we have a point charge Q. Now, By considering this point charge Q as a center, imagine a spherical surface having radius equal to small r. Now, on this particular surface, at any point, if you calculate the potential due to this point charge Q at the center, then you will get KQ upon R. At any point on this spherical surface, the potential that will be the same one, that is KQ by R, KQ by R, KQ by R. It implies that we can say this particular spherical surface, that is the equipotential surface for this given charge, or we can say for the given electric field of this given charge. Clear to all of you? Now see, for equipotential surface at each and every point, the potential is same one. It implies that for any 2 points on the equipotential surface, we can say the potential difference is 0. Suppose on equipotential surface, we take 2 points A and B. Then we can write the potential difference between A and B, that is VB minus VA. No doubt that is equal to 0. But as discussed in the previous theory, the potential difference between these 2 points, that is minus integration A to B E dot dr. Clear? Now suppose we consider this displacement of unit positive charge dr, that is very small. It implies that point A and B are very close to each other. Then simply we can write the potential difference between those 2 points, that is equal to minus E dot dr. એક જ સ્ટેપ લેવાનું. આપણે ઇન્ફાઇનાઇટ ડિસ્પ્લેસમેન્ટ્સ બધા લઈને એનું સમેશન કરતા હતા, એની જગ્યાએ એક જ ડિસ્પ્લેસમેન્ટ માટેનું એક જ સ્ટેપ. તો that is minus E dot dr. But A and B both are at the same potential. So potential difference 0. But E dot dr, that is E dr cos theta, and that is equal to 0. But here E is non-zero, dr is non-zero. It implies that cos theta, that is equal to 0. And therefore we can write theta, that is equal to pi by 2. તો એનો મતલબ એવો થયો કે electric field at any point on the equipotential surface is perpendicular to the surface. Is perpendicular to the surface. So here, for uniform electric field, we can prepare the equipotential surface which is perpendicular to the electric field, and that will be the plane surface. Clear to all of you? Now the next topic, that is relation between field and potential. Suppose here we have 2 equipotential surfaces which are separated by distance delta L, as you see in the figure. Here one equipotential surface, that is surface A, for which the potential at each and every point, that is V. Another equipotential surface, that is B, for which the potential at each and every point on the surface, that is V plus delta V. So in short, we can say the potential difference between these two surfaces, that is equal to delta V. Clear to all of you? Now, here, if we calculate the work done against the field on moving the unit positive charge from surface B to surface A, or we can say, let's calculate the work done to move unit positive charge against the field from point P by delta L. Then we can write that work done, that is E delta L, that is equal to the potential difference, that is final minus initial. Initial position, that is on surface B. Final position, that is on surface A. So VA minus VB. But potential at the surface A, that is V, then minus potential at the surface B, that is V plus delta V. If we simplify this one, then we will get E delta L, that is minus delta V. So we can write E, that is equal to minus delta V by delta L. Okay. Now we can write in the vector form electric field E, that is equal to minus delta V by delta xi caret plus delta V by delta yj caret plus delta V by delta z k caret. So we can write this one like this also. Electric field E, that is equal to Exi caret plus Eyj caret plus Ez k caret. So if we compare these two equations, then we can say the differentiation of potential with respect to x and negative of it will give you the x component of electric field. Then negative of the differentiation of potential with respect to y, that will give you the y component of electric field. And differentiation of electric potential with respect to z, it will give you z component of electric field. Okay. And if your potential, that is constant one, then simply you can write E, that is equal to V by D, or V equal to E into D. This one is the relationship between electric field and electric potential. Clear to all of you? Now, potential energy of a system of charges. See, we already discussed this thing. What is the concept of electric potential and electric potential energy? Now, electric potential energy of any charge at any point in the electric field, that is nothing but the total work done against the field to bring that charge Q from infinity to that particular point. હવે જો આપણે કોઈ આખી સિસ્ટમની પોટેન્શિયલ એનર્જી આપણે ડિસાઇડ કરવી હોય તો શું કરવું પડે કે આપણે આખી સિસ્ટમની અંદર જેટલા ચાર્જીસ છે એ બધા ચાર્જીસની એસેમ્બલી તૈયાર કરવા માટે જે ટોટલ વર્ક ડન કરવું પડે એ કેલ્ક્યુલેટ કરવાનું. અને એ total work done to assemble that entire charge system will give you the potential energy of that particular system of charges. Say, suppose we have a system of 3 charges, or we want to assemble a system of 3 charges. Okay. Now, we have to bring these 3 charges Q1, Q2 and Q3 one by one from infinity. And in that particular process, we have to calculate the total work done against the field. Now see, very first we bring charge Q1 from infinity to point 1 as shown in the figure. Point 1, that is at the position R1 from the coordinate, origin of the coordinate system. તો ચાર્જ Q1 ને તમારે point 1 પાસે લઈ આવવા માટેનું જે total work done છે ને એ 0 થશે. Why? Field જ નથી. There is no field. Therefore, the work done to bring charge Q1 from infinity to point 1, 0. Clear? Any doubt in this one? Now, bring charge Q2 from infinity to point 2. But when we bring charge Q2 from infinity to point 2, at that time charge Q1 is already there. It implies that, in other words, we can say we are placing charge Q2 in the electric field of charge Q1. Okay. So here the total work done, that is potential at point 2. So potential of charge Q1 at point 2, that is, suppose V1. So the total work done, that is W2 equal to Q2 into V1, where V1, that is, as per equation KQ upon R, we can write KQ1 upon R12, where R12, that is the distance between Q1 and Q2. Clear? Then after, we can say, now the total work done to assemble a system of 2 charges Q1 and Q2, so that is W1 plus W2, and that work done will be stored in it in the form of potential energy. So we can write W1, that is equal to 0, and W2, that we calculated K Q1 Q2 upon R12. So simply we can say the potential energy of a system of 2 charges, that is K Q1 Q2 upon R12, that is the distance between those 2 charges. This one is similar to that the gravitational potential energy of a system of 2 masses, Gm1 M2 upon R12. Clear? Now here, if Q1 Q2 is greater than 0, then we can say the potential energy is positive, and if Q1 Q2 is less than 0, means potential energy is negative. Now suppose here a third charge Q3 is brought at point 3 from infinity. Then total work done is how much? So work done, that is potential at point 3 into Q3. પણ હવે Q1 અને Q2 બે ચાર્જ હાજર છે અને તમે થર્ડ ને લાયા છો, તો Q1 નું પોટેન્શિયલ at point 3. So we can write here potential of charge Q1 at 3, that is V13. Then potential of charge Q2 at 0.3, that is V23 into Q3. Now Q3 into potential of charge Q1 at 0.3, that is KQ1 upon the distance between 1 and 3, that is KQ1 upon R13, plus potential due to charge Q2 at 0.3, that is sorry, KQ2 upon R23, the distance between 2 and 3. So we can write now resultantly this work done, that is equal to K Q1 Q3 upon R13 plus K Q2 Q3 upon R2 3. Clear to all of you? So we can say the total work done to assemble the system of these three charges, that is W equal to W1 plus W2 plus W3. So that total work done is stored in it in the form of potential energy. Now W1, that is equal to 0. Then W2, that is K Q1 Q2 upon R12. And W3, that is K Q1 Q3 upon R13 plus K Q2 Q3 upon R23. And this one is stored in it in the form of potential energy. So now we can say the potential energy of the system of these three charges, that is U equal to K Q1 Q2 upon R12 plus K Q1 Q3 upon R13 plus K Q2 Q3 upon R23. In short, તમારે શું કરવાનું કે તમને ગમે તેટલા ચાર્જ વાળી સિસ્ટમ આપી હોય અને તમારે જો આખી સિસ્ટમની પોટેન્શિયલ એનર્જી ગણવાની હોય તો તમારે જેટલી પોસિબલ પેર્સ હોય ટુ 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 ચાર્જીસ વાળી એ બધી પેર્સ માટે પોટેન્શિયલ એનર્જી લખી ને એનું સમેશન લઈ લેવાનું. That will give you the resultant potential energy. What is